Welcome back. In lecture 42, we will talk about route choice. So, the different concepts that we will cover in this particular lecture will be route choice in the context of trip assignment, then minimum spanning tree, Kruskal which we will solve using Kruskal's algorithm and Prim's algorithm, and then we will look into the shortest path methods, and within that we will use two algorithms which are minimum tree algorithm and Dijkstra's algorithm. So, this is what we will cover in this particular lecture. So, when we in the last lecture we have discussed that once we know the trip volumes between two zones, after that the next step that we have to perform is to determine which route would be used by the users in, of course, the vehicles to travel from one zone to another. So, the route determination is first and then the link assignment happens. So, when we do the route assignment, and then users are assigned to a network based on some underlying assumptions based of route choice. Now, what are these assumptions? Now, Wardrop in 1952 established two principles of route choice, and both these principles are mutually independent, and he actually gave idea about two form of equilibriums. One is user equilibrium, another is system equilibrium. Now, in the first one, he says that users choose a route which minimizes their travel time. So, whenever a user chooses a route, he will choose a route which minimizes his or their travel time, and no user will be able to lower their transportation costs further by changing their action. So, that is the first thing, and when this happens, the journey time in all the used routes between these between this origin and destination pair are all equal, and because different users may feel different paths are the shortest, and accordingly they will take that, and less and all the other routes where there is are equal and less than the journey time by a single vehicle in any unused route. So, that means all the other routes which are unused, there the journey time is higher. So, this is the concept which leads to user equilibrium. That means, when everybody wants to go to a route which he thinks to be the shortest, then automatically there would be a few routes which are having the same amount of time that would be taken by all those different routes, and any routes that are not chosen will have a lesser travel time. So, this is the first user equilibrium principle, and the other is talks about system equilibrium, where users distribute themselves so that each interzonal travel time for all users is same. So, that means users will distribute themselves so that the overall system travel time is the least. Now, this total cost of system is minimized, and equilibrium can be achieved by marginal cost road pricing or central routing control. That means that when the city actually tries to determine that how to give equal impedance and so on. So, that means they will introduce some road pricing schemes, or they may do some control of the traffic signals at the central level, and in that way this could be achieved. So, this is how system equilibrium could be achieved. But as you can understand, in most cases we end up with the user equilibrium, because system equilibrium is both difficult to achieve and also it is not based on behavioral principles, because people do choose routes which they feel are the shortest or whatever based on the information they have got and so on. So, we have another variant of the user equilibrium, where users choose a route which he perceives to be the shortest. So, users do not have full knowledge. They have incomplete knowledge of networks and modes, or at that particular point in time what is the situation, and accordingly they choose a route which is they perceive to be the shortest. So, that is not based on the actual cost. So, that is based on his perceived cost. So, this leads to stochastic equilibrium. So, these are three ways users choose a route. So, before the actual assignment can happen, we need to identify first, and also before that, whenever we are talking about usual equilibrium and all, we are talking about assignment. That means the user would be assigned to a particular route, and in what order or what sequence they would be assigned. But even before that, we need to identify set of routes which might be considered attractive to the drivers or the users. So that means whichever he feels perceived to be the shortest one. So we use two type of algorithms. One is the minimum spanning tree, and the other is shortest path. These are some of the algorithms which are used to determine this routes in terms of cost. So that means when we try to determine a route, first of all in terms of cost, and we determine in two ways. That means we may either look at a shortest path, that means between two particular points, or we may try to decide a route which actually covers a certain number of points. So these are two different algorithms that we are actually going to study. So a number of factors are thought to influence the choice of route when driving between 2 points. So how do we determine the cost? It could be based on journey time, it could be based on distance, it could be based on monetary cost like fuel and other cost, it could be based on congestion and the queue cost, and the type of maneuvers required in that particular route depending on the route structure or the road conditions maybe, and type of road, motorway, trunk road or secondary road. Some people are comfortable going in secondary roads, some people are not, they want to go by arterials and main roads only. Then scenery, signposting, road work, reliability of travel time along that particular route, and also based on users' habit. So these are the different things when people may consider when they choose a particular route. But usually two factors are most important, as you can understand. One is time and the other is monetary cost of traveling along that particular route. So the reasons affecting the route choice decision of different drivers also vary. For example, there is difference in individual perceptions. Some may wish to minimize time, others wish to minimize fuel consumption, and many a combination of both. So that actually leads to many route choices. So even though everybody wants to go along the shortest path, but definition of shortest path actually differs in different individuals. That is why when we are talking about this usual equilibrium, because people choose different shortest path, actually it leads to a form of equilibrium where the number of users choosing different paths will actually balance itself. Then the level of knowledge of alternative routes varies across individuals, that also is true. And then congestion effects affecting shorter routes first and making the generalized cost comparable to initially less attractive routes. Now suppose there are two routes, in one the travel time was 10 minutes and the other the travel time was 12 minutes, but once many people start getting into the first route, automatically it becomes congested, so the travel time now increases to 13 minutes. So that other route becomes more attractive. So that is also a reason why the shortest path also change over a time within a time period, and that actually leads to also choice of different routes. So first we will look into the minimum spanning tree algorithm, and this actually leads to identification of attractive paths for drivers, and that also depends on, of course, the lowest cost. Cost could be both money or time both, and but the objective remains that we need to visit all nodes, or it could be also to reach a particular node. So that both could be solved by a minimum spanning tree. Now a basic spanning tree is a spanning tree of a graph. A spanning tree of a graph with n vertices is just a subgraph that contains n vertices and n minus 1 edges. It ensures connectivity of a network with minimum number of links. That means in a big graph which has got n vertices, we determine a subgraph, that means a smaller graph, and which contains n vertices. That means we will have n vertices and n minus 1 edges. So we will have less number of edges, but the vertices that we will touch all the vertices. This ensures connectivity of a network with minimum number of links. That means we are able to go to each particular node by traveling the least number of links. Now a minimum spanning tree, which is MST, And here what we do is we consider weights of each of these particular links. So we suppose edges of the graphs have weights or lengths, and weight of a tree is just the sum of the weight of its edges, and the tree with the minimum weight is the minimum spanning tree. So there could be many spanning trees connecting between different nodes or connecting all the nodes in a particular graph, but there could be only one, there could be some minimum spanning tree which would be lesser than the total number of spanning trees, and where the cost is least. And this minimum weight could be determined through different, so this minimum could be determined by using different algorithms, and shortest road network to ensure connectivity of all nodes. So this is the what we are trying to solve. Some classical minimum spanning tree algorithms are Kruskal's algorithm and Prim's algorithm. So two criteria of a minimum spanning tree is possible multiplicity. That means there may be several minimum spanning trees of the same weight having minimum number of edges and if all weights are same, every spanning tree is minimum. So that means if we give the same weight to all the edges, then all the spanning trees will have minimum weight. That is understood. And at the same time, we can say if the weights vary, then basically we will have many, we can have or may not have many number of minimum spanning trees. But if each edge has a distinct weight, then there will be only one unique minimum spanning tree. So that is called uniqueness property. So that means if each edge has got separate weights, like in this particular case, we are having a network of A, B, C, D nodes, and this is the different links, and these are the impedances where we have given these impedances which are all different. So this will lead to only one minimum spanning tree which is given in this particular figure. So Kruskal's algorithm, the first algorithm that we will consider, this is a greedy algorithm, and here in a graph with n vertices, we will keep adding the shortest or the least cost edge while avoiding the creation of cycles, that is a closed loop, until n minus edges have been added. I will discuss that using an example, but the steps in what it means is in a graph with n nodes, n vertices, we keep adding the shortest or the least cost edge. So we will select the least cost edge, and we will keep on selecting that till a cycle or a closed loop is formed and until n minus edges have been added. Because there are n nodes, so there has to be n minus edges to create a minimum spanning tree. So that means we will keep on doing that until n minus 1 edges have been selected. So the steps are we take a subgraph S of G which is initially empty, there is no links in the subgraph S, and so then we sort all the edges of G in an increasing order by length. Then we choose the shortest edge, and for each edge E in the sorted order, if the endpoint of E's are disconnected in S, add E to S. So that means in that S subgraph, if it is as long as it is disconnected, we will keep on adding this shortest edges, and then finally we will return to S, the first step. So in this example, you can see this is the first part. This is the graph which includes this A, B, C, D, E, F vertices, and each one is having a particular cost or a weight, and in this one we choose this particular edge which is having the least cost, which is 1. And then in the next step we will choose the edge which is of least cost, we choose 2, and we see that this is not completing the cycle, or which is not completing the graph, and also n minus 1 edges are yet to be chosen. So we have only chosen 2 edges. Then we go into the next step. There we add the next, we have another link edge which is 2. We could have taken the other one as well, but we can always go one after another, and this is the second one. And then the third one is we choose the edge which is 3, which comes after 2, and this still doesn't complete the S subgraph. So there is because there is a break over here, so we select this, and in the next iteration we have got 4. We have got 4 over here and we have got 4 over here. So if we choose this 4, then the cycle would be completed. So we don't choose this one, so we choose this one. So ultimately we have our minimum spanning tree, which is like this. This is how it looks like. So this is the total minimum spanning tree. The weight is 2 plus 3 plus 1 plus 2 plus 4. 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is the total weight of the spanning tree. So in the next algorithm, in Prim's algorithm, instead of building a subgraph with one edge at a time, Prim's algorithm builds a tree with one vertex at a time, which that means it will take one vertex and consider it as a tree. And so in other words, Prim's algorithm treats the nodes as a single tree initially and keeps on adding new nodes to the spanning tree from the given graph, and it is we follow certain rules with that. For example, the first step is to remove all loops and parallel edges. That means we look at a graph and we will remove the loops that are there or the same parallel edges. So this is more relevant when we have already done some iterations. Then there are some cases when we are returning back to the the previous node, and that creates a loop, and that has to be avoided. So remove all loops and parallel edges, then choose any arbitrary node as root node. We can start with any one of the nodes. Then check outgoing edges and select one with the least cost. So from this particular node, all the edges that are connected, we will choose the one with the least cost, and then we will grow the tree by one edge using the minimum weight edge out of the edges that connect the tree to the nodes not yet in the tree. That means all the open-ended nodes which could grow further, we will choose the one which has got the least weight, and we will grow the tree in that direction. We will step 4 is continued until all vertices are traversed. Until all the nodes are covered, we will keep on doing that. So actually this is a variant of the previous algorithm, Kruskal's algorithm. There we were choosing edges, but here we are choosing nodes, and we are expanding from the nodes. So let's show an example, explain with example. Over here you can see we start with this particular network. We have got A, B, C, D, E, F, 6 nodes, and these are the impedances which are given. So we start with any one of the nodes. Let us start with A, and so we choose the link which is the edge which is the least cost, which is 1. So we have chosen this, we have not chosen 4, and from 1 now we have got 2 open edges. At A we can expand in this direction, from B we can expand in this direction, or we can also expand in this direction. So definitely from B we can choose out of all these 3, like 3, 4 and 4, 3 is the least, so we will choose 3. So we have chosen 3 over here. So this is number 3. So this is 3 is chosen. Now the open edges are A and C. So this is 4. From C we have got 6, but if I got, and then from B this is another edge, we can also have 4. Now if I choose from A, then it completes this cycle which cannot be taken. So we will choose to expand in this particular direction, because in over here it is 6, within 6 and 4, 4 is lower, so we choose 4. So this is how we have expanded, and then we have got open edges which is E, C, A, and even in this direction 5. So over here we see that the least cost is 2, and that's why we have chosen 2. And then finally we come over here, where from F we are seeing that we have 1. None of the edges are smaller than that, so we will choose 1. So this gives us the minimum spanning tree which has got, which is connected A, B, C, and then B to E, and F, and then D. So this is the actual minimum spanning tree. So these are the 2 algorithms that we can use for determining minimum spanning trees. So now we come to shortest path, and in shortest path method we are trying to find a path between 2 vertices or node such that the sum of the weights of its constituent edges is minimized. So this is what we need to determine. That means between any 2 nodes, what is the shortest path or what is the sum of the weight of all the constituent edge when it is minimum, that is what we have to determine. So, two important characteristics of the shortest path are a subpath of a shortest path is also a shortest path. That means, because we are already on a shortest path, we take any one of the paths that would be a shortest path in between these two nodes. And if a graph G contains a negative weight cycle, then some shortest path may not exist. That means that shortest path, this will not work if there is a negative cycle in the graph. Negative cycle means there is a loop. When you add that loop, the total weights leads to a negative value. So, that is a negative cycle. So, consider a graph where G is equal to VE. So, V is vertices and edges, and edge weight function is W, and the weight of the path, that means the shortest path P includes V1, V2, these are the different vertices, and for the directed graph can be defined as weight of P, weight of this path is equal to summation 1 equal to 1 to k minus 1 this W into V1, V1 plus 1 and so on. So, in this way we will determine the weight of a path. This is just a representation, and shortest path from U to V is a path of minimum weight from U to V. The shortest path weight from U to V is defined as in this way, delta UV is minimum of weight of path and P is path from U to V. So, a minimum of all the paths, and this one becomes infinity if no path exists from U to V. So, if there is no path, then the cost is maximum, then the cost is infinity. So, if this is the assumption, then that is why in the different algorithms that we use, we always assume that if it is there is no shortest path, it is the value is infinity, and if I can find a shortest path, then we will replace that value of infinity with a value which we have found for impedance for that particular path. So, first we will discuss the minimum tree algorithm, and this will lead us to the minimum shortest path. So, this is sort of a tree algorithm, but it leads to the shortest path between any two vertices, and this could be described numerically by a tree table. A tree table contains, so this is a tree table, and the tree table contains all network nodes J including the origin, the total impedance of minimum path from the origin to each node J, and the total and the node I that immediately precedes node J on the minimum path from origin to node J. So, for suppose we the total impedance of minimum path from the origin to each node J. So, that means let us assume the origin is 1. So, origin 1 to node 1, origin 1 to node 2, origin 1 to node 3, this is the total impedance for this particular node along the shortest path. So, that is what is listed in the tree table, and we also list that what was the preceding node. Now, because we are listing the preceding node, we would be able to build the tree. For example, for going from 1 to 5, the total shortest path is 12. And let us see over here, 1 to 5, the shortest path should be along in this particular way. So, this is 3, this is 2 and this is 7, because if we go along this direction, this is another path that is possible. So, this is 4, this is 4, this is 7. So, together this is 12 and together this is 15. So, of course, this is the shortest path. So, that means, so 1 to 5, the shortest path is 12, that is listed over here in the tree table, and the previous node is 4. So, from 5 the previous node is 4. Now, I go to the table where the shortest path of 1 to 4 is given. So, here I find the impedance is 5 and the previous node is 2. So, I know that my shortest path is 1, in between 1 to 5 there is 4, and in the fourth table there is 2. So, 1, 2, 4, 5 is the shortest path. So, this is how we interpret a tree table. So, this is the starting point. Now, minimum tree algorithm can produce a tree table to determine all interzonal minimum paths emanating from zone of origin. The algorithm is given as follows. I will go through the algorithm, but at the same time it's better to explain using a actual example. So I will explain that. I will just go through the steps. Step 1 is initialize the path impedance of the tree table, 0 for node of origin and a very large number for all other nodes. So I was just discussing it, like whenever we are starting with a shortest path problem, if we don't know there is a shortest path, we say it's having a infinity value. So we can start with infinity and 0 for the node of origin. That means from we take the first path as 0, that is the starting point, and all values from this particular node to all other nodes as infinity. So this is the starting. Then enter into the list the links ij that emerge directly out of node I, added to the tree except the ones which form a cycle. So from, suppose we have the same network. So this is 1, 2, 3, 4. So from 1 we will list the nodes 1 to 2 and 1 to 3. So once we do that, so we list the links 1 ij that emerge directly from node 1 added to the tree except the ones that form a cycle. If there is one, if this actually completes a cycle, we will not include that. So that we will have to take care. And then for each node j included in the list, add impedance of link ij. So we will determine the link ij impedance. So suppose it is 3 and suppose it is 4. So we will list that, and the total add the impedance of link ij to the tree table's current total impedance to node I. So because this is the first time we are estimating, so that's why we are this is replacing infinity and we are putting 3 and 4. But this, if this already has a value from our earlier iteration, we would have replaced that particular value with this current value. And if this value is smaller than the current tree table, we will add this new value, and we will replace the longer path to node j with this shorter one just discovered right now. Otherwise, we will reject the option and proceed to the next link in the list. From the list of links ij, node j is added to the tree. So we will keep on we will choose the minimum link, and then we will keep on moving from this path. So and we will take each of this link, and then we will keep on expanding the tree, and then again we will try to find in the same way, and return to step 2 unless the link is empty. So we will return to step, we will do it continuously till the entire list is empty. So let's see by an example. So this is the we are trying to determine the minimum tree for this particular network. So this is the same network that we have shown in the earlier lecture. So this is the these are the centroid nodes 1, 2, 3, 4 and so on. These are the links. This is a bidirectional link, and we are getting the impedance of each of this link, and that is also represented in this particular scheme matrix. So that is this zone from 1 to 6, the impedance is 5. So 1 to 6, the impedance is 5. And similarly from 6 to 1, this impedance is 5. Then from 6 to 7, 6 to 7, impedance is 8. And from 7 to 6, so all this, whatever we are seeing in this particular network is loaded over here, or you can say if we get this particular values, we can also draw our particular network. So once we do that, once we have drawn our network like this, we start with link 1, which is in this particular case we are starting with link I1, and then we are seeing the first link is till j, which is 6. So that is being listed over here. So the total impedance we determine, which is given as 5 from our earlier table, and 5 is lesser than infinity, so we accept that. And then we go to the link 6, because we have now arrived at 6. Now from 6 we expand the tree. We can expand in 3 directions. It could be towards 7, it could be towards 10, it could be towards 9. So that is what we have listed. Now we compute the final total impedance till this particular point from the starting point. So it would be 5 plus 8 for 7, which is 13, which is less than infinity, we accept. Then 5 plus 5, which is again 10, which is less than infinity, we accept. Then for link 10, that means from 1 to 10, link, this node 1 to 10, the total impedance is 9. So we accept it because it is less than infinity, and so on. Now for each of this 7, 9, 10, we keep on expanding. So we from 7 could be expanded to 2, 6, 8, 10. So, from 7 we can go to 2, we can go to 8, we can go to 10, and we can also go back to 6. Now, going back to 6 actually creates a cycle or a parallel loop. So, it is a parallel line back. So, we will actually reject that. So, we have computed the value that it, because we can add like because we can always we can directly reject it, but automatically it will get rejected because we are returning back and we are adding a new distance, that is the impedance 7, to the previous distance which was 13. So, automatically it would be lesser than the previous distance to this particular node, which is 5. So, that is why it also gets rejected in that particular way. But straightforward we can reject it because it completes a cycle or a link, or this it is a parallel link. So, when we are talking about link 7 and to 2, that means we are going towards this direction, then we are adding the impedance of 2. So, it is 15, 15 is less than infinity, we are accepting. Then same for till link 8, we are saying 13 plus 4, so that becomes 17. So, we initially had 13, that is link 7, the values of 13 is final. So, 13 is now added to the impedance for this 7 to 8. So, we get 17, we accept that, and so on, we are accepting it. And then when we are talking from coming to 9, 9 to 6, this is where is 9, this is 9, 9 to 6 is again a parallel link back. So, we are rejecting that, and then for the other two we are estimating, and then from 10 we are having 10 to 6, 10 to 6. So, when we go to 6 we get around 16, but already this 1 to 6 we know. So, which is 5. So, that it is lesser greater than 5. So, we reject that. So, we keep on doing this, and at one point you will find that there is all links emanating from this the final nodes 3, 4, 5, 11, 14 are rejected to avoid formation of cycles, and that is the point we will end. And from this particular tree we can actually write down the total impedances 1 to 6, 1 to 7, 1 to 9, 1 to 10, and in so on. We can write that we will find the like 1 to 7 is 13, over here 1 to 7 is 23. So, obviously 70 this one is better. So, we keep that, and so in that way we will choose the list impedances and we will create the tree table. So, 1 to 1 is 0, 1 to 2 is 15, 1 to 3 is 21, 1 to 4 is 18. We will pick it up from this particular table, and we will also take the preceding node also from this particular table, because we have the preceding node 1 to 2 is 15, preceding node is 7. So, that is how we have picked that. So, this is how we can create the tree table, and from here we can also compute the shortest path. So, this is a graph based method. This is one algorithm for determining shortest path between any two vertices in a particular network. Then we look into another algorithm which is called Dijkstra's algorithm, and this algorithm solves a single pair, single source and a single destination shortest path problem. So, this means that it will start from 1 and also end with, so any one single pair to another destination, it will actually determine what is the shortest path. So, it does not determine shortest path from one origin to all the destinations, it will determine to shortest path from one to one destination. So, in this particular algorithm, we start from we can start from any vertex. Let us consider I as the start vertex in the network. We will set I as 0 and the distance to all other vertex as infinity, similar to the previous algorithm. Then we will visit the unvisited vertex with the smallest known distance from the start vertex. So, suppose I have a network. So, this is my start vertex. So, I will reach the vertex along, these are 3 and 4. So, I will choose the one which has got the least distance. So, I will choose this particular vertex. So, that is what is said. So, visit the unvisited vertex with the smallest known distance from the start vertex. So, all the unvisited vertex, this is the smallest known distance. From the current vertex, like over here, examine its unvisited neighbors and calculate the distance of each neighbor from the start vertex. So, from here we can go over here. If there was a link like this, I could have gone over here. So, in that case, I will also determine the impedance from the start vertex. So, this is 1, or suppose this is 2, and this is 3. So, from 3 to 3, this becomes 6, and then over here, and then over this side, this is 3 plus 2, this becomes 5, but already the value is 4. So, we will not accept 5, we will keep it as 4, and now we have got over here this is 4, and here that is 6. So, this is the smallest vertex, we will start from this side. So, this is the process that we follow. And if the calculated distance of the vertex is less than the known distance, update the shortest distance or update the previous vertex for each of the updated distance. So, we also need to take care of which was the last vertex that was recorded, and return to step 2 unless the list of unvisited neighbors is empty. So, let us see an example. So, over in this particular example, in this particular graph, we have got, so we have got A, B, C, D, E, F. These are the 6 vertices. And then let us start with A. So, we set A as 0 and all the other vertices as infinity. And we also create this table where we have got listed all the vertices from A, B, C, D, E, F. We choose A as 0 and all the vertices as infinity, and we have also a column for previous vertex. So, visited vertex A. So, first we are visiting A. Then from A we can go in 3 directions. We can either go in this way, or we can go in this way, or we can go in this way. So, these are the 3 directions. So, out of that the shortest direction is in this one, 7. So, we will write 0 to 0 plus 7 because this was 0. So, this is 7, this is 9, and this is 14, but the shortest is 7. So, because it is shortest, we will fix that. So, we have earlier visited A. So, we will list for all this 7, 9, 14, these are the previous vertices, and this 7, 9, 14 are the the impedance to this particular vertices from A. So, in the next step, because 7 is the shortest, we will choose 7. From 7 we can go in 2 directions, we can either go here or we can go here. So, we now have got this new impedance computed. So, which is impedance till B plus the new link impedance. So, 7 plus 15, which is 22, which is less than infinity. So, we keep 22. Then 7 plus 10, which is 17. Now, 17 is greater than 9, which was computed earlier. So, we will keep it as 9. That means, the shortest path to reach C from A is 9. It is not through B. So, we will keep it as 9, and then we have got, and this remains as 14 because we are not able to reach. So, now we have got these 3 new edges which are like 22, 9 and 14. So, and we also we have written the previous edge, like for 22 the previous edge is B, and for D the previous edge is A. For this particular shortest path, the previous vertex is A, and so on. So, in the next step, because out of all this we need to choose this one. This is the shortest one. So, from here there are 2 options, either we can go in this direction or we can go in this these 2 directions. So, this was 9, this was earlier chosen, this is now fixed. So, 9 plus 2, this is 11, which is lesser than 14, which was earlier estimated. So, we choose 11. So, we replace 14 with 11. So, this is replaced, and from 9 to from C to F, now it is 9 plus 11, that is 20, which is also lesser than 22, which was chosen earlier. So, we replace 22 with 20, and the previous edge becomes C. So, these 2 are fixed. Now, these 2 are now put over here. So, in the next step, out of all this we can see this is 20, this is 11, and this is infinity. So, we will choose 11. So, D becomes fixed. So, over here D becomes fixed. So, 11 becomes fixed, and in the next step we have got E, which is 11 plus 9, which is 20. So because it is less than infinity, we have chosen that. And over here, so this is only one way we can go. So we have replaced and the last vertex and the previous vertex from E is D, so that we have listed, and everything else remains same. And then from E, we can go till F using this path 20 plus 6, 26, which is greater than 20. So this doesn't becomes the shortest path. So it remains 20 remains as the shortest path. So this is my tree table, you can say, where we have determined the shortest path from A to all the different vertices, A to A to B, A to C, A to D, A to E, and A to F. So basically we can determine the shortest path from F, and we have to go to F till C, and that means from A to F we reach like this. So this is the shortest path. So this is how Dijkstra's solve shortest path. And finally, so at F there is no more shortest path to go. If there is no more new vertices, unvisited neighbors are there, so we end over here, and that's the end of this particular algorithm. So we are able to determine all the shortest path over here. So in addition to Dijkstra's algorithm, which can only consider positive weights, there are other algorithms which can also consider both positive and negative weights. But as you can understand, there is that problem of this negative cycle when we consider negative weights, that is an issue still. So we have this Floyd-Warshall algorithm. So this is a dynamic programming algorithm to determine shortest path in a negative or positive edge-weighted graph, unlike Dijkstra's algorithm, which is functional only for positive edge-weight graphs. Now, why we have not, we can study this, but in a transport network, in most cases we will have a positive graph. That means there is additional impedance for each link, so there is no negative weights as such. So Dijkstra's algorithm is good enough to solve that. And then another important feature of this algorithm, but Floyd-Warshall algorithm could be used if there are negative weights in a particular graph. And another important feature of this algorithm is the shortest path from I to j is determined for all pairs I, j of vertices in a graph, and not just from a spatial single source like Dijkstra's. Because in Dijkstra's we are starting from one single source, and then we could find the shortest path to any of the other edges, whereas over here we can find the shortest path between different edges. And in addition, we have got another algorithm, which is Bellman-Ford algorithm, which is a little bit slower in terms of computation times compared to the Floyd-Warshall algorithm. And shortest path is calculated between two vertices in a weighted graph, where some edge weights are negative numbers, similar to the previous algorithm. But the benefit of this algorithm is this can detect negative cycles. That means in Floyd-Warshall algorithm, we cannot detect negative cycles. So that is one issue. But here it can detect negative cycles, and that is a benefit of this particular algorithm. So these are some of the references you can use. And to conclude, route choice is an essential step in the trip assignment process. Then minimum spanning tree and shortest path are some of the strategies used by individuals to choose routes. And there are various algorithms are used to reduce the computation time for determining shortest path or minimum spanning trees in a complex network. So some of the algorithms we have studied. So you can also study other algorithms as well. Thank you.